Hey there, lovely people. My name is Samira Sayed. I'm currently pursuing my BE from Sri Venkateswara College of Engineering, first sem. My USN is 23CS2042. Today, we'll be discussing about the applications of partial derivatives. These are the contents we'll be going through. Introduction. Partial derivatives are an important concept in multivariate calculus that allows us to analyze how a function changes with respect to one variable while holding other variables constant. It is a way of breaking down a multi-dimensional problem into a smaller, more manageable problem. In simple terms, it measures the rate of change of a function in one direction while keeping all the other variables constant. Let's look at an example now. Find the partial derivatives f of x and f of y for the function f of x comma y is equal to pi x to the power 4 minus x square y square plus 2x cubed y. Solution. We have our initial f of x comma y is equal to pi x to the power 4 minus x square y square plus 2x cubed y. Now to find f of x comma y, we keep y as constant and differentiate the initial given f of x comma y. We get 20x cubed minus 2y square x plus 6y x square. Similarly, to get fy of x comma y, we keep x as constant and differentiate the initial given f of x comma y. After differentiating, we get minus 2x square y plus 2x cubed. Now let's look at a real-world example of partial derivatives. The ambient temperature somewhere in California depends on where the temperature is counted. Therefore, the magnitude of the temperature needs to be expressed in the mathematical form of T of x comma y comma z comma t, in which the variables x comma y and z in the function t indicate the location at which the temperature is measured, and the variable t indicates the time of the day or the month of the year at which the measurement is taken, the rate of change of the magnitude of the temperature. Example, the derivative of the function t x comma y comma z comma t needs to be dealt with the change of each of these four variables accounted with this function. In other words, we may have altogether four such derivatives to be considered in the analysis. Each of these four derivatives is called a partial derivative of the function t x comma y comma z comma t, because each derivative, as we express mathematically, can only represent part of the derivative for this function that involves multivariables. There are two kinds of independent variables in partial derivatives. One, spatial variables represented by x comma y comma z in a rectangular coordinate system, or r comma z in a cylindrical polar coordinate system, and we have the temporal variables represented by time t. Applications. Partial derivatives are used in various fields of mathematics and science, including calculus, physics, engineering, economics, computer science, etc. Application of partial derivatives is crucial in solving real-world problems by providing valuable insights into the behavior of complex systems. With advancements in technology and computing, the use of partial derivatives has become even more prevalent in data analysis, machine learning, and artificial intelligence. Therefore, understanding and effectively applying partial derivatives plays a significant role in various disciplines, making it an essential concept in modern mathematics. Now let's look into the applications of partial derivatives within mathematics. We have the multivariable calculus, Partial derivatives play a central role in multivariable calculus, allowing for the study of functions with multiple independent variables. In multivariable calculus, we often encounter functions that depend on two or more variables, such as f of x comma y or g of x comma y comma z. To differentiate these functions with respect to a particular variable, we use partial derivatives. The partial derivative of a multivariable function with respect to one variable is denoted by del, pronounced partial, followed by the variable name. For example, the partial derivative of x of f of x comma y with respect to x is written as del of f by del of x. Similarly, the partial derivative of g of x comma y comma z with respect to y can be represented as del of g by del of y. By calculating these partial derivatives, we can determine how the function changes as we vary each input variable individually while keeping the others constant. This information is valuable in fields such as physics, engineering, economics, and many others. Geometry, by considering how a function changes with respect to different variables. Partial derivatives allow us to investigate properties such as gradients, tangents, planes, and curvatures of surfaces in three-dimensional space. One area where partial derivatives are particularly useful is in the study of surfaces. By these partial derivatives, we can determine the orientation and curvature of the surface at that point. Furthermore, partial derivatives enable us to quantify the rate of change of geometric objects. For example, the partial derivative of a curve's parametric equations can give us insight into its arc length and curvature. These measurements provide valuable information about the shape and behavior of curves, aiding in the understanding of their properties. Differential equations. Partial derivatives are used extensively in the study of partial differential equations. PDEs arise in many areas of mathematics and physics, and partial derivatives help analyze their solution. When solving PDEs, partial derivatives are typically used to transform the original differential equation into a system of ordinary differential equations. This conversion paves way for employing various analytical and numerical techniques applicable to ODEs, making the solution of partial differential equations more tractable. In addition to their application in transforming PDEs, partial derivatives are also used to derive other important results in differential equations. Optimization. In optimization, problems involving multivariables, partial derivatives help identify critical points that correspond to maximum or minimum value of a function. Taylor's series expansion. Partial derivatives play a crucial role in Taylor's series expansion. The Taylor series expansion represents a function as an infinite sum of terms, each term being a product of the function's higher order partial derivative evaluated at a specific point and the corresponding powers of the variables. By taking partial derivatives of a function, we can determine the values of these derivatives at a specific point. These values are used to compute the coefficients in the Taylor series expansion. The higher order partial derivatives capture the behavior of the function at that point, allowing us to approximate the function using a polynomial equation. The more terms we include in the expansion, the closer our approximation is to the original function. In summary, partial derivatives provide information about how a function changes with respect to each variable separately, which enables us to construct accurate approximation through Taylor series expansion. Thank you for being here.